Hey guys. All right. Today we're going to look at limits at infinity. Previously, we looked at limits to infinity. And those were the ones where we had something like, might help if I plug in my tablet. Okay. Those are situations where we had like the limit as x approaches c from the right of some function would equal infinity. And then the limit, let's say, as x approaches some c value from the left of that same function equaled negative infinity. And in these situations, we were talking about vertical asymptotes. So notice in both of these situations, we're approaching some c value. So our f of x function could have been something like 1 over x subtract 3. And we might be looking at what's happening as we approach 3 from the right and what's happening as we approach 3 from the left. And we know from studying rational functions in precalculus that we have a vertical asymptote at 3. From the right, it's going to positive infinity, and from the left, it's going to negative infinity. Well, what we're going to do now is we're going to look at something a little bit different. We're still looking at limits that are involving an infinity, but now we're looking at limits as x approaches infinity and analyzing what's happening with our functions. So when we're doing this, so we're looking at limits as x is approaching positive infinity and negative infinity, we're actually looking at our horizontal asymptotes. So you'll remember from pre-calc, so recall from pre-calc that whenever we did that, we would look at our function. We would say, okay, we have a to the m power over a to the nth power. And we could have a whole big long polynomial in the numerator and the denominator, but we only cared about our leading terms, and more specifically, really the leading exponents of our leading terms, right? And then we looked at how they compared to each other. So we said, well, if the exponent in the numerator is less than the exponent in the denominator, so if my exponent in the numerator is less than the exponent in the denominator, which means that the one in the denominator is greater, this n, then we said that our horizontal asymptote would be the line y equals 0. If we had the reverse situation, so if n was greater than m, this was a situation we didn't love because this involved some type of oblique or some other type of function, essentially. We had to end up dividing and figure out what exactly that asymptote was. But in this situation, we noticed in pre-calc that our limits for positive infinity and for negative infinity of that function went to either positive or negative infinity in both situations. So when we had an oblique asymptote, when our degree in the numerator was 1, oh, I wrote that wrong, didn't I? M greater than n. So when our degree in the numerator was just 1 more than the degree in the denominator, we always had a linear function, and that linear function was our asymptote. And so our as we went to positive infinity, it would either be going, our function would either be going to positive infinity or negative infinity. And then conversely, as we went to negative infinity, it generally went to the opposite, depending on that multiplicity. The last situation is when m equals n. And when m equals n, oh, sorry, let's change this to a b. We had a ratio. So we said, well, these are both getting large at the exact same rate because this m, these exponents are equivalent to each other. And so when this occurs, our limit as x goes to positive or negative infinity of some function is going to be just a over b. The only thing we have to be careful with is sometimes we can have more than one horizontal asymptote because remember, unlike vertical asymptotes, we can cross a horizontal asymptote. It's not as like forbidden to cross as that vertical asymptote is. So we just have to be careful with that. So what we're going to do today is we're going to kind of step away from the pre-calc and apply the calculus. So we're going to look and apply limits to all of these. And we're going to analyze them analytically, but we're also going to think about them theoretically about what's actually happening. And from that, you should have two ways to be able to understand these. You should be able to look at it at the end at the beginning and say, I'm expecting this to be the result. And then analyze it analytically and see if what you were expecting matches what actually happens after you do out the algebra. So let's kind of think about the big picture real quick. And this is going to involve a lot of what we did over here. So when we say that it's growing faster, so if we say that our denominator grows faster, it means that we might have a large number, but not a number as large as what's in my denominator. And then we have an insanely large number in our denominator. So we have something like infinity squared in our denominator, and maybe we just have infinity in our numerator. Because that denominator is getting large at a faster rate, this is a situation where we have a horizontal asymptote where my denominator is getting really, really big. This is really small, so we're doing like 1 divided by a trillion. That's going to yield 0. If the denominator and the numerator grow equally fast, that's the situation where we have m equal to n. They're growing at the same rate. Then we have a ratio of a over b. So we have some ratio as a result. And then if the numerator grows faster than the denominator, then you have an insanely big number in the numerator, not so big number in the denominator. So when you divide those, it's going to divide out to either be a positive or negative infinity, depending on the signage. So let's just take a look at this kind of theoretically. In order to kind of analyze this, we need to have a good idea of how fast some of these functions grow. So what we're going to do, we have 1, 2, 3, 4, 5, 6, 7 different functions here. So we're going to number these 1 through 7, where 1 is the fastest. So this is increasing at the fastest rate, and 7 is going to increase at the slowest rate. So that one's going to be the slowest. So what we want to do, we don't want to look, notice that x equals 1, a lot of them share a common value, right? 1, 1, 1, because we're just putting 1 into these polynomials. Notice that e to the x is 2.718, so it's slightly larger than 2 to the x, but less than 4 to the x. And then for ln x, when we put in 1, we get 0, because e to the 0 power is 1. The first thing that sticks out to me, so I'm going to go from 1, and then I'm going to go all the way to when my numbers are getting a little bit larger. So notice that I have 10 to the 6th, 10 to the 9th, so they're getting increasingly larger. I have 1.07 times 10 to the 301st. That's significantly larger than x to the 10th power, right? Even though at x equals 10, notice that x to the 10th power is larger at that point, right? 10 to the 10th is much larger than 1024. But as we approach x to the 100th, x equal to 100, notice it starts to surpass that x to the 10th, and then ultimately is significantly larger in this instance. E to the x is a really big number, but 4 to the x, because this base of 4 is larger than 2.718, notice that 4 to the x is an insanely large number. And then ln x is kind of slacking here, right? And if you think about what the natural log of x looks like, it still increases without bound, but it really has a very low, not steep, the opposite of steep, a very gradual slope as we continue on and go to infinity. So I'm going to start here. We know that this is going to increase at the slowest rate, right? And then this number is insanely large. That's going to increase at the fastest rate. Next up, we have e to the x, and then 2 to the x. So notice these situations where I have a base other than 1, obviously, and obviously all these are greater than 1, which makes a big difference. So I have a base that's greater than 1 to the x power. Those are going to get larger at a faster rate than any of our polynomial functions where I have a base x raised to just a single power, because those kind of level out on us. But then if we only have these types, if we only have polynomial functions here, the larger the degree is going to mean that it's getting faster. It's getting larger at a faster rate. So then we're just going to kind of go 4, 5, and then obviously x squared is going to be our slowest. All right, let's do some practice problems. All right, so I have a number of problems here, and what we're going to do is I'm going to drag them to the front, and you can write them down in your notes as we go through them. We're going to determine the limit at infinity for each function. And in some situations, we'll be able to just do it once, because if my degree in the numerator is equivalent to my degree in the denominator, my degree in the numerator is greater than the degree in the denominator, that's going to be going to 0. And 0 doesn't have any polarity, right? So whether I'm going to positive infinity or negative infinity is not going to make a difference. I know my horizontal asymptote in that situation is going to be y equal to 0. But I just want to show you how we work through some of these. So let's start with this first one. We have, bring it to the form. Oh, no, it's not going to let me. We have y equals x squared plus 4 all over 3x minus 5. So I'm going to analyze this. This is example 1. I'm going to find the limit as x goes to positive infinity of x squared plus 4 all over 3x subtract 5. Now I'm going to do a little trick here, and the only reason I can do this trick is because this limit is going to infinity. I don't want you to think that you can do this if we have x going to some c value. The only reason this works is because I'm putting insanely large numbers in for x. And because I'm putting insanely large numbers in for x, this plus 4 and subtract 5 are meaningless. This is like if you are a billionaire and you lose 4 cents on the subway. You're not really going to notice that you lost 4 cents. But if you have no money to your name and you lose that 4 cents, that's going to make a big difference, right? So it's all perspective. So because we're going to infinity and not something like 2 or 3, we can just kind of pretend that they're not there because they're negligible. So I'm going to rewrite this limit as the limit as x goes to infinity of x squared over 3x. So what I did was just take the leading terms. So I took the largest degree term in my numerator and the largest degree term in my denominator. Now I'm going to notice that I can do some canceling, right? So I have an x squared and an x, so this cancels down to a 1. This goes away. I'm left with the limit as x goes to infinity of x over 3. Well, if I put infinity into this function now, I'm going to get a positive infinity back out. So I find out that the limit as x goes to infinity of this function is going to be infinity, which means my horizontal asymptote is probably going to be, especially since my degree is 1 greater in the numerator, is going to be some type of oblique or slant asymptote. I'm going to have like a linear function there. Let's look at this now. Going to the left. So the limit as x approaches negative infinity. So again, we have x squared plus 4 over 3x subtract 5. Well, we know that this is going to be equivalent in this case. I'm just going to skip a step here because we've already done it, to x over 3. Well, now if I put negative infinity in here, a negative divided by a positive is going to give me a negative. So this is going to equal out to be a negative infinity. So I have some horizontal asymptote, and as I'm approaching, not horizontal, I have some oblique asymptote, and as I'm going to the left, as x is getting larger and larger and larger, my y values are getting more and more and more negative, and they're also approaching infinity. All right, now notice this Desmos graph. So this is the graph of the function that we just took the limit of to analyze its end behavior. And notice as it's moving to the left here, these values are getting closer and closer to negative infinity, and we can zoom out and see that in fact they do just get more and more negative, and then going to the right they get more and more positive. So we have some type of oblique asymptote that is some linear function between here acting as my horizontal asymptote. All right, let's take a look at this next one. And these ones can be a little bit challenging because they involve square roots. So we're going to first look at the limit as x approaches positive infinity of the square root of 4x squared plus x subtract 2 over 3x subtract 1. So the first thing we're going to do is the same thing we did in the last problem. We only care about these leading terms. So I'm going to ignore all of that because it really just doesn't matter when you get down to infinity. So we have now the limit as x approaches infinity of the square root of 4x squared all over 3x. Now we need to take a minute to talk about what this square root of 4x squared means. Obviously, we can take the square root of 4x squared, right? We take the square root and we can get 2x. The only thing we need to be careful with is that this number needs to be positive. And if I were to put a negative value in here, or sorry, the output of this value needs to be positive. And if I were to put a negative value into here, I would get a negative output. So it's really important that I put absolute value signs anytime I take the square root of an even degree, because I want to make sure that my output is positive and not negative. And it's very important when I have an even degree, which then results in an odd degree after I take the square root. Because again, there's no way for the answer of the square root of 4x squared to be negative, since we're dealing with, from the original problem, the principal root, which is positive. You could put anything you want in for x right here and take the square root. You're always going to get a positive out. So I need to force this expression to be positive, and the way that we do that is with absolute value signs. So now I'm going to go ahead and analyze this. I have 2 times infinity over 3 times infinity. Notice that these are getting large at the exact same rate. So what this is going to end up yielding is 2/3. I'm not going to eliminate my absolute value here. I'm just going to analyze it as it is. Now let's look going from the other direction. I have the limit as x approaches negative infinity now. And again, we're doing the square root of 4x squared plus x subtract 2 all over 3x subtract 1. Now again, I'm going to go ahead and eliminate this extra stuff. And then I'm going to take the square root. So this now equals the limit as x goes to negative infinity of the absolute value of 2x over 3x. Now notice what happens when I sub in. When I put the negative infinity here, they're still getting large at the same rate because their degree is exactly the same. The only difference here now from the previous problem is that this numerator has to be positive, and we talked about that in the previous example. But this denominator does not need to be positive, so this is going towards negative infinity. But again, they're increasing at the same rate, so they're canceling out, but that negative still holds true. So this is going to equal a negative 2/3. So what you would see with this function is you would see 2 horizontal asymptotes at y equals 2/3 and y equals negative 2/3. And if you want to, you can go ahead to Desmos just so that you can kind of see it for yourself. But you'll see that there are 2 horizontal asymptotes in this problem. All right, the next one's going to flow a little bit more nicely. So we're going to do the limit as x goes to infinity of x plus 4 over 3x squared subtract 5. So if I think back to algebra, to pre-calc last year, the degree in the numerator is less than the degree in the numerator. This is like our traditional situation. In this case, I should see that I have a horizontal asymptote of y equal to 0. So let's kind of analyze it analytically and see what happens. So we have the limit as x goes to infinity. I'm going to get rid of this extra. I'm just going to care about these leading terms of x over 3x squared. I'm going to simplify down. This is going to leave me with a 1. This is going to leave me with just a 3x. So I now have the limit as x goes to infinity of 1 over 3x. Well, notice what's happening now. If I put infinity in here, I have 1 divided by an insanely large number. So if I do 1, if you don't believe me, put it into your calculator. 1 divided by 1,000,000 is going to get you a number really, really close to 0. So this is approaching 0, which means that my horizontal asymptote is equal to y equal to 0. I don't need to analyze this limit from the left for the sole reason that I'm going to run into the same exact situation. Even if I'm putting in negative infinity, 0 does not have any polarity, so I can't have a negative 0. I'm still approaching 0. I'm just approaching 0 coming from below rather than from above. So it's just going from a different direction. All right, our next one is also, oh, did I skip? I think I skipped one. All right, we have the limit, sorry, this third example, x approaches infinity of x plus 4 over 3x subtract 5. Again, we're going to disregard the plus 4 and the negative 5, and we're just going to analyze the limit as x approaches infinity of x over 3x. Well, notice the degree in the numerator is equivalent to the degree in the denominator. So I can go ahead and cancel out. And this is just going to simplify to the limit as x approaches infinity of 1/3. Well, that's a constant, so it's just going to be 1/3. So I know my horizontal asymptote in this situation is y equal to 1/3. So I don't need to analyze the limit as x approaches negative infinity because I know that I'll still get 1/3 out. All right, we have 2 left. Let's take a look at the limit as x goes to positive infinity. This is another one that involves a square root, except notice now the difference here, I have a degree of 1 here and I have a degree of 2 in my denominator here. So we have 4x to the 4th plus x subtract 2 all over 3x squared subtract 1. And then we're also going to analyze the limit as x approaches negative infinity of 4x to the 4th plus x subtract 2 all over 3x squared subtract 1. All right. So again, we're going to follow a similar process. We're going to exclude these. Do that over here for now. So now I'm looking at the limit as x approaches positive infinity of the square root of 4x to the 4th all over 3x squared. I'm going to go ahead and take the square root. So I have the limit as x approaches infinity of 2x squared. I'm going to include the absolute value, but it's really not necessary because if I put a negative value in here, I'm going to get out a positive. I just do it habitually so that I don't forget it in that one instance, especially under a stressful situation, but it's really not necessary in this case, all over 3x squared. So if I put positive infinity in, these are getting large at the exact same rate, and so we end with 2/3. Over here, I'm going to follow the same process. I have the limit as x approaches negative infinity. I'm going to jump to this step because I know it's the same thing. Right, I'm plugging in negative infinity, but because I'm squaring both of them, they're turning into a positive, so I'm still going to get out 2/3. So my horizontal asymptote in this situation would be y equal to 2/3. All right, in our last example, I wanted to put this one on here because it's starting in a form that's not really beneficial to us as we analyze the limit at infinity. You need to make sure that if you have a problem like this, you multiply out first. So notice I can't cross cancel anything. That's unfortunate. So I'm going to go ahead and I'm going to multiply out. I'm going to get x squared plus 3x subtract 10. And I'm going to get 16x squared. What's that? 1224. Subtract 24x plus 9. I really didn't need to do any of this because it doesn't matter. The only thing I care about are these leading terms. Oops, that's an infinity. So I'm taking the limit as x goes to positive infinity of x squared over 16x squared. I can go ahead now. I'm going to throw a 1 there. These two can cancel out because they're getting large at the exact same rate. And I'm left with, for my answer, this equal to 1 over 16. And that will also be true for negative infinity. So I can state that my horizontal asymptote, there's only one, is going to be y equal to 1/16. So notice the only time we couldn't write out what the horizontal asymptote was when in that first example, when my degree was larger in the numerator than in the denominator. And that's because I don't have a horizontal asymptote in that situation. The situation where you have as the limit as x goes to infinity and negative infinity is also going to infinity and negative infinity. So it's getting large without bound in the y direction as well. In that case, we have something called either an oblique asymptote, or sometimes that could even be a quadratic or a cubic function. They can take on a variety of different forms depending on the difference in the degrees. And in those situations, you would need to divide to be able to find the equation of that line. But we're not going to get into that. All right, the last thing we're going to look at for the notes is, I think I might have one more page after this. Let's see. All right, let's just take a look at when we have e to the x. So this first example is the limit as x goes to positive infinity. So we're not finding the horizontal asymptote in this situation. We're just looking to analyze this limit. And we have negative 4e to the 1 over x. So I'm just going to rewrite it in my own handwriting because that makes more sense for me. 1 over x. And so we're substituting infinity in for x in this denominator. So I have 1 over an insanely large number, which means this is going to 0. E to the 0 power is 1. So this is going to equal negative 4. In the next example, I'm doing the limit as x goes to infinity of 5e to the negative x. I'm going to go ahead and rewrite this. So I have the limit as x goes to infinity of 5 over e to the x. So notice this e to the x is getting very, very large. We saw that already. It gets to be an extremely large number as x goes to positive infinity. And so we have 5 divided by an insanely large number. And so this one is going to 0. So you really have to analyze each situation on its own because these look like two very similar problems, but they result in two very different answers. There's no like one size fits all. All right. All right, the last section that we need to look at is when we're looking at trig functions. And just as usual, these are a little bit different just because of the nature of what a trig function is. So what we're going to do is use the squeeze theorem to help us with these, just like we used previously for trig functions. So when we have the limit as x approaches negative infinity of sine of x over x, I'm going to start this off by saying that I have sine of x and that sandwich between 1 and negative 1. And now I'm going to divide everything by an x. And then I'm going to take the limit as x goes to infinity everywhere. All right, so now the limit as x goes to negative infinity of negative 1 over negative x is going to give me 0. The limit as x goes to negative infinity of sine of x over x is what we're trying to figure out. And the limit as x goes to negative infinity of 1 over x is going to also be 0. So we can conclude by the squeeze theorem that that limit is equal to 0. Let's do the same thing here. Cosine 1 over x, that's going to live between negative 1 and 1. I'm going to multiply everything by negative 3. And remember, so we have this. This is a reminder from Algebra 1, and then you may have seen a little bit in Algebra 2. When we multiply an inequality by a negative, you have to switch the signs. So we have 3 now is greater than or equal to -3 cosine 1 over x, which is greater than or equal to -3. I'm going to rewrite this so it's going in the correct direction. That means we have the limit as x goes to infinity. I multiplied everything by, okay, is greater than or equal to -3 cosine 1 over x, which is greater than or equal to the limit as x goes to infinity of 3. Oh, I didn't switch this. It's the little things you notice. All right. There we go. So now we're sandwiched between these. As x goes to infinity, this is going to remain -3. This is also going, no, this is, that's not going to work. Let's do this.